Okay, so today we're going to look at how do we handle integrals that have a rational expression. And there are like a whole bunch of different possibilities of what could happen here. We're going to go through five. The first one we're going to call factoring and cancel. Okay, so this is assuming that part of this is actually factorable. An example of this would be the integral from like x squared plus 5x plus 6 over x plus 3. This is going to reduce to x plus 3 times x plus 2 over x plus 3, which means these cancel out, giving me the integral of x plus 2 dx. Okay. And ultimately, this is going to reduce to 1/2 x squared plus 2x plus c. All right, so that's probably like the easiest situation that we contend with here is something where we have a a removable discontinuity. We just remove the discontinuity and we end up with, boom, everything works. All right, so let's look at another example. Okay, our second method here is going to be long division. Okay, and the way we handle long division is, so this is like a very similar, these things are going to look a lot alike, right? But the method is going to change here. So now I'm no longer factorable. Top is not going to factor. So I take the numerator, x squared plus 5x plus 7, divide that using long division by x plus 3. So let's see, if I take x times x plus 3, that's going to give me x squared plus 3x. And I subtract these. So it's 5x minus 3x is 2x, and then bring down, right? So we're just using the long division algorithm. And then we take 2 times this, gets me 2x plus 6. We subtract these, gives me a remainder of 1. So this is the same as the integral of x plus 2 plus 1 over x plus 3 dx. That's the result of the long division here. And then we just take the antiderivative. So we get 1/2 x squared plus 2x plus the natural log of the absolute value of x plus 3 plus c. And there we go. We have an antiderivative. It's not like the obvious response to this, but this is a way to move forward. Okay, so a third way to move forward on something that is a rational, or an integral with a rational expression is using, we've seen this before, use substitution. So let's say I have the integral of x plus 3 over 2x squared plus 12x plus 4 and dx, right? So we let u be 2x squared plus 12x plus 4. That means du dx is 4x plus 12, which means that dx is du over 4x plus 12, right? So this is the integral of x plus 3 over u times du over 4x plus 12. And lo and behold, if I pull a 3 out of this, I'm going to get 1/3 there. Those will cancel out then, giving me du over u, which means I have 1/3 times the natural log of the absolute value of u plus c, which should be 1/3 times the natural log of 2x squared plus 12x plus 4 absolute value plus c. And there you go. I have an antiderivative using u substitution. Okay, so by far the most interesting of these methods is what we're going to call using partial fractions. And this is something that is specific to the BC exam. These don't come up on the AB exam. So we're going to take the integral of x plus 5 over x squared plus x minus 2 dx dx. So if I factor the bottom here, I am going to get x minus 1 times x plus 2 dx. Now, sorry, this should be not x plus 2 up here. This one should be still x plus 5, right? So that's a 5. Let's make sure that we understand that that is a 5, right? 5. There, whatever. All right, so let's do some thinking here. What we're going to do is we're actually going to try to unbake the cake here. So we know that x plus 5 is x minus 1 plus x plus 2 could have come from a sum of something over x minus 1 plus something else over x plus 2. Okay? Like if you think about this, the common denominator of this is this. Okay? So if you multiply through by that denominator, you're going to get x plus 5 is equal to a times x plus 2 plus b times x minus 1. And if I distribute that, I'm going to get x plus 5 is equal to ax plus 2a plus bx minus b. If I rearrange this, I'm going to get x plus 5 is ax plus bx plus 2a minus b, which means x plus 5 is equal to a plus b x plus 2a minus b. All right, so what does that give me? Well, the coefficient in front of the x is 1. So a plus b has to equal 1. The constant has to be equal to this, so 2a minus b has to equal 5. Now I have a system of two equations with two variables. The easiest way to progress here, I think, is by elimination. If I combine these two, I get 3a is equal to 6, which means that a is 2. And if I substitute that 2 back into the first equation, I get that b is negative 1. Wow, okay. So this gives me a new way of writing my integral. Because my integral is, well, a is 2, so that's 2 over x minus 1 plus, well, b is negative 1, so that's going to be minus 1 over x plus 2 dx. And this is pretty straightforward. This is just like 2 times the natural log of the absolute value of x minus 1 minus 1 times the natural log of x plus 2 plus c. And there we go. By using this strange partial fractions method, I end up with an antiderivative. So we're going to let you kind of hang with that for a little bit. I'd advise possibly like going back through this section of the video to make sure that you follow what happened there, because these problems will come up on the BC exam because they are BC specific. Okay, so the last method here is about inverse trig functions, specifically the inverse tangent, right, and the inverse sine. Remember that the antiderivative of 1 over 1 plus x squared is the inverse tangent, and the antiderivative of 1 over the square root of 1 minus x squared is the inverse sine. So let's say I have x over square root of 1 minus x to the 4th. Okay, the hint that this is an inverse sine problem is that square root hanging out in the bottom there. So let u equal x to the 4th. This is going to give me du dx is 4x cubed. Sorry about that. That's not what I want to do. That's going to make a mess. Let's let u equal x squared. Aha, there we go. So du dx is equal to 2x, right? Which means that du is equal to dx over 2x. All right, so this is going to be x over the square root of 1 minus u squared. We just got it in the right form for the sine inverse, right? Times du over 2x. The x's here cancel out, so this is 1/2 times the antiderivative of du over square root of 1 minus u squared, which is 1/2 times the sine inverse of u, plus c, which is 1/2 times the sine inverse of x squared plus c. And there is my antiderivative. Okay, so you want to look out for things that could be potentially inverse trig functions. So here's 5 different techniques that you can use when you see some sort of rational expression in your integral, and hopefully this is helpful.